Good morning, I'm Dave Ullman. Dr. Seeley, appreciate the invitation to speak. Appreciate the invitation offering me 15 more minutes. I'm going to talk about USTOL a lot. USTOL is a term you're probably not familiar with. Dr. Seeley wanted me to make this eSTOL, but it's a little different. You'll also notice the airplane there. That's clearly a doctored picture, but that's my Jabiru, well, really legally a Jabberwatt that I'll get into. And there's a lot of funny things happening on the leading edge that I will explain to you. My background, started out in aerospace engineering, ended up in product design, taught that for many, many years. I'm a retired professor. As you'll see, this project is totally self-funded, which is one of the benefits of being an emeritus professor. You can just do what you want. I built a couple general aviation airplanes. I've been thinking about and working on electric airplanes since 2009. Wrote a couple articles. One thing you learn as an academic, if you want to learn about a subject, you either teach a course in it or you write a paper about it. So in 2009, I wrote this Hear the Hum paper for kit planes, and it was basically, you need to have a motor, you need to have a controller, you need to have batteries, all these basic things. Followed that up with another article that got a little bit more detail. Then I had this Velocity aircraft that didn't cool very well. I went off into vortex generators, which ties in here a little bit. And then after I attended the Uber conference last year down in Dallas, I came away scratching my head because, I'm hearing all this stuff about eVTOL and all this stuff, and it did not quite seem to click right for me. So I went and did some studying on this. So it ended up with a paper that you can get off my website called Comparing Electric Sky Taxi Visions, which is basically I'm going to cover in this talk. And I had some contributors, Vince Homer. Vince, raise your hand. He's my partner in crime here. And also had Pat Horgan of Cub Crafters, who we met at the Uber conference last year, and also Richard Ouellette, who we met there also. Richard does not officially represent Boeing, but he had a lot of input. So in 2015, Vince and I started to really begin to study the USTOL potential, and some of our credentials are that we don't know if this is a bug or a feature. We have about 100 years of combined engineering and making things work experience. So the things we do are really quite practical. And interestingly enough, he did some research work on the Custer Channel Wing back in the 1970s. How many of you know what the Custer Channel Wing is? You'll all know what it is in a few minutes because we sort of started there. We have a patent application on this USTOL concept. That'll become clear as we go. One of the beauties of this, we're totally self-funded. Some of you may want to change that. If so, we're here to talk about it. Do be aware, I've been the DARPA SBIR route. I've been the NSF funding route. I don't have to do that anymore. I've started 2 businesses and failed miserably at both of those. I don't start businesses anymore. So what's our goals here? I'm going to tell you what an UltraSTOL is. I'm going to show you an analytical model I developed to compare the rotorcraft, eVTOL, and UltraSTOL. You hear all these. I just listened to 2 days of Uber presentations. I did the LinkedIn online, and I heard I saw these really beautiful pictures and all this great stuff. And I have a little BS monitor in the back of my head, and I kept vacillating between how much was BS and how much was really possible. I don't want to be an old fogey and say, hey, you can't do all this stuff. I want to be over the bleeding edge. That's a good place to be, but I want to know where the reality is. And so there's a lot of reality in this talk. So this model that we developed, it's really quite simple, and I'll get into more details, but basically, if you tell me what class vehicle, eVTOL, rotorcraft, or USTOL, you tell me what class, you tell me the number of passengers, and you give me the battery capabilities, I can calculate what the range, power required, and vehicle costs are going to be. It's pretty rough, but it can give you some really good ideas of what direction you should be heading in. Okay, so then we're going to make the case that this USTOL concept, which you still don't know what it is, but I'll get there, that it really has some potential, and we ought to be doing some more work there because it fits a lot of the visions that I've heard already this morning. And then we'll give you a peek at what we're doing. So that's what I'm doing. I was reminded after listening to the Uber conference and realizing that I was totally out of step with them, I was reminded of this quote from Benjamin Franklin. So, Ben Franklin didn't exactly march to all the drummers either. So, classes of aircraft we're going to consider is rotorcraft, eVTOL, and USTOL. We all know what rotorcraft are. There's a whole bunch of really interesting ones out there. We'll come back to the Robinson 44, the Epsilon project a little bit later, but in case you're not familiar with that, on pure electric power, it stayed up for 30 minutes. Okay? Had one person on board, but stayed up for 30 minutes. We're all familiar with the EHang and the eVTOL that are under development, but this is the class of what I'm calling rotorcraft. The eVTOL could have picked a lot of pictures. Both the Lilium and the Trifan are both actual hybrid. They're not purely electric vehicles, either one of them, but Uber is very adamant that they want pure electric. And so in this talk, we don't really touch on hybrid at all. Everything we're talking about is pure electric. But these two examples I put up there were just good examples. So let's worry about what USTOL means. Okay, so here's a very well thought out definition of USTOL. And basically, it's a winged aircraft. It uses distributed electric propulsion. We've already heard about that this morning. It creates propulsion airframe interaction. This is a key thing because if you just take an IC engine out of an airplane and you put an electric motor in, you've missed an awful lot of the potential benefit. The key is, can you use the distributed propulsion to actually enhance the aerodynamics? And I don't think this has been very well researched yet. And so that's the direction we've gone off onto. Two examples of this are the Custer channel wing, which is shown in the lower left. That's one of the instantiations of it. And the Boeing YC-14 shown in the lower right, and there have been others. So let me explain to you what these airplanes were doing and what makes them unique. So first, let's worry about the Custer channel wing. This was his last airplane. He started, a guy named Willard Custer started thinking about this in 1939 or so. And this is an airplane that's in the mid-60s someplace. This is the CCW, Custer channel wing, CCW-5. And what he basically did was make an arc out of part of the wing and put the engines in that arc, and the engines suck the air over the wing. Here's a fairly good representation of it, and it increases the air velocity over the top surface of the wing. Now the reality is that your lift generated on an airfoil, about 80% comes from the top surface of the wing. And so if you increase the velocity over the top surface, let's see, Bernoulli said it's velocity squared. So if you double the velocity over the top surface of the wing, you got a factor of 4 increase in lift. Seems to have some potential. So I don't know why more people aren't looking at this. This is a really great photograph. This is the best version of it we could find on the web. What this is the Custer channel wing. Let's see, I even think I got here you can see the channel, the little stubby wings, because this is one of his earlier ones. He didn't even think he needed those, but the authorities insisted that he put some wings on it. This thing is tethered to a pole and tethered to the ground, but you might notice it ain't touching the ground. This thing is lifted its own weight. Now, admittedly, it doesn't have a pilot in it, but still, this is lifting its own weight. I find this an amazing photograph. There's a really great quote from Willard Custer. It's the speed of the air, not the airspeed. And the first time I heard that, it sounded sort of trite. But then the more I thought about it, and the more I started playing in the wind tunnel and doing some work, the more I realized that's a pretty good quote. So anyway, the YC-14 was from the 1960s. They were responding to a request for short field takeoff transports. You'll notice that I got to get the laser point. You notice the engines are in really, really close to the fuselage. Anybody that's flown a twin-engine airplane know that the engine-out situation is really bad. Here it's even much worse because not only is your thrust asymmetrical if you lose an engine, your lift is asymmetrical. So things get really bad. So you better keep those engines in really tight. Over here is a cross-section. This is in a takeoff mode. You can see the flap is down. Notice that the flap is down almost 90 degrees because the air coming out of here is at such a velocity, and with some vortex generators, they can get the flow to wrap around and almost give them a downward force. So pretty amazing aircraft. There's still one in a museum and one sitting out in the desert someplace of the two that were built. So let's keep on STOL. This is not a USTOL. This is Little Cub. Little Cub at the Valdez. Watch it take off here. He's starting at the white line. Watch his main landing gear. And he's getting ready to release it. There he goes. Boom. Okay, ignore the ad. I couldn't get rid of that. And now watch, he's going to land. His goal is to land beyond the white line, but as short as possible. Okay. Takeoff, 14 feet 7 inches. Landing, 10 feet 5 inches. Total score, 25 feet. Now, yeah. Now, in defense of reality, he did have a 15-knot headwind. Okay, I know. Cheating a little bit. But, and there's a couple other things. First of all, this airplane has virtually no cruise speed. It gets up at a steep altitude when it takes off. Weight, he's got everything stripped off this airplane. Typically, these Valdez guys are flying in their underwear and they've dieted the day before because they want to get the weight just as low as they can. He's got, I think, an IO 320 in it that he's jacked up really high. So I have no idea what horsepower he's getting out of that thing. And he's a very skilled pilot. He's been doing this 15 years, 20 years. So, you know, we'll never get down to 25 feet, but it can be done. And in fact, oh, by the way, I forgot this part. I call this brute force STOL because that's what he's really doing. But there are commercially available airplanes. Here's the Carbon Cub from Cub Crafters. They've demonstrated with a stock airplane, 60 feet takeoff, 53 feet landing. You know, this is sort of like the Little Cub, but this is a real airplane, and it can do it. So this is a basic formula for takeoff distance, okay? And it's really quite simple. It just says, if you've got the wing loading, which is the weight over the area, and if you got the thrust over the weight, and this is the lift coefficient for takeoff, okay? You can either lower the wing loading, but that gives you a penalty during cruise. You can add more thrust, okay, or you can raise the lift coefficient on takeoff. And the YC-14 had these big flaps blowing the jet over. Coanda effect made the jet exhaust stick to the flaps, push down, raise the lift coefficient on takeoff. So Little Cub sort of tried to do this in a crude fashion, but. So one last thing, this is not a USTOL airplane, but this is NASA's X-57. And what's cool about it is it's using distributed electric propulsion. Do keep in mind that all these intermotors here are only used for takeoff. They've reduced the wing area so small they can't get off the ground unless they get some more air flowing over it. And so there are propellers that unfold on each of these, and then they fold up when you're in the cruise mode. But they're not making real good use of the propulsion airframe interaction. They're just blowing the air over the top and bottom surface of the wing. And I think we can do even better than that. So I've introduced some terms to you. I didn't mention the term upper surface blowing, but that's basically what the YC-14 is doing, is blowing over the upper surface. There's lots of other technologies that have been tried in the past. With a distributed electric propulsion, some of these technologies need to be revisited because they have really great potential now that they didn't have before. So that's the definition of the UltraSTOL. We're using ducted fans, electric ducted fans, and together we came up with this wonderful acronym, which I dislike, which this is what we're calling our project, the Integrated Distributed Electric Augmented Lift, but we never say that, we just say that's the ideal. And you'll get more ideas about what ideal is in just a few minutes. So this is a picture from our patent application. It basically shows an airplane with some ducted fans along the top surface. They're obviously just trying to accelerate the air over the top surface. We can get takeoff lift coefficients greater than 5, and I've been very conservative here, and L over D's at cruise well over 20, and so we think this has great potential. Yeah. So, as I said before, the speed of the air over the top surface is 80% of your lift. So, and we're using these little ducted fans. What's interesting is the model airplane industry has started making pretty good quality small ducted fans. The ones we're playing with right now, such as this one, is 120 millimeter diameter. It claims to be able to produce about 16 pounds of thrust. We have one on order. It's back ordered. When we get it, we're going to do a whole lot of measurements on it and see what it'll really get. It's about 4 kilowatts in power. So this is a picture here from our wind tunnel experiments. Again, being self-funded, if I need a tunnel, I build it. And so Vince and I built a wind tunnel. It's got a 2-foot by 2-foot cross-section, fully instrumented. We have smoke generation. We can get all kinds of really good data. This, you can see, there's really 3 ducted fans on here. They're only 50 millimeter. They're little. They have a very low energy density, so we run 3 of them. This is a rather simple airfoil up on the stilts, which measures all the forces. So, to finish out this idea, this is a typical velocity versus thrust curve. This is actually for a stock Jabiru airplane and an LSA, 1,300-pound airplane. But if you can get the airflow over the top surface of the wing, get some flap area, get some better lift at the low conditions, you can actually modify that curve. And what this basically says is that if you normally, let's say you had 100 foot-pounds of thrust in these units, you could get off the ground much, much sooner with this technology. And if you lower the wing area and play some other games, you can actually get the curve down to the green curve. And if you can get down to the green curve, you got a pretty efficient airplane. So I'm going to come back to this in just a second. I want to segue into the analytical model that we used. And I mentioned earlier that we have a model. This is a spreadsheet model, which, by the way, if you want a copy of it, happy to share it. It runs on Excel. And basically, if you put in the max range, it'll calculate the max range, gross weight, et cetera. And all you need to do is tell it which of the 3 classes you want, the energy density and kilowatt hours, and the number of occupants. By the way, when I use the word occupants and passengers interchangeably here, I just mean souls on board. I don't care whether there's a pilot and passengers, just the number of warm bodies that are 100 kilograms in this model, 220 pounds. So, for those of you that have an aerodynamics background, there's fairly well-known Berger's range equation, which was done in the 1950s for internal combustion type or even jet. And a number of people have extended that for electric. Rob McDonald and Brian German did it last year for Uber, and then I realized this year that Rob McDonald's now an Uber employee, so there's hope for me yet. No, I don't want a job. So we exercise this model across 3 different classes of battery. The current reality, about 150 watt-hours per kilogram. The near future, and don't ask me how far the near future is, I'm not a battery person. And then the far future, which is 450 watt-hours per kilogram. And so basically, if you want to know the total energy capacity here, you got to take the battery weight times the energy density times the percent deliverable, And as you'll see in a later slide, we used 80%, but that's probably high, and we'll get to that in a second too. And so Bourget's equation is basically based on weight fractions. And so we broke this down into the airframe weight fraction, the passenger weight fraction, the battery weight fraction. It has to add up to unity. So the airframe motors and controllers, we started out at 55%. The more I exercise it, the more I think this is a little high, but not real high. The passengers, you specify the number of passengers, and this is the weight we use. So once you know the total weight, you can divide that into this and find the weight fraction. The battery weight fraction you have to take apart, because for the USTOL, you need to have taxi and takeoff. For the VTOL, the eVTOL and the rotorcraft, you need to have hover. All of them need to climb, cruise, descend, and have a reserve. And so what you do is, we built formulas for all of these things, and then you take what's left and put it into the cruise so that this ends up equaling 1, and what's left is how much battery you have left to cruise the airplane, because all these other things have to happen. Okay? So I made a whole bunch of assumptions here, and in the interest of time, I'm going to let you read those. I'm only going to hit the high points. One is the electrical propulsor efficiency. Propulsor efficiency, propeller, 85% seems to be pretty standard used, and your electrical system's in the 90% range, so the product of those two is the 76%. These assumptions, by the way, closely follow McDonald and German, and I only deviated from them when I thought they were really wrong, but they're fairly reasonable assumptions. A couple more is when you have a hovering aircraft, you need a figure of merit, and that's just the ratio of the ideal power required to the hover power required, and you got to multiply that by the electrical system efficiency, so that comes out to 63%. Hover time's an interesting one. McDonald and German used 60 seconds. I went with that. You could argue that if you got a vertical takeoff, you don't really need to hover for 60 seconds. You could just go. Don't know. You got to make some assumptions to get some answers. Reserve time's real interesting. If you look at the FARs, you need 30 minutes day, 45 minutes night. That's not realistic for these. It'll be interesting to see where it comes down. We use 10 minutes. I mentioned earlier about the percent availability, and they used 80%. My electric car buddies have all said 60% is probably more realistic. So again, if you are interested, I'll send you the code. You can put in any numbers you want and see what it tells you about vehicles. This is a really hard slide, and I don't want to take a lot of time on it, but the other information you need for this model to work is you need to have some idea what is the lift-to-drag ratio for climb, lift-drag ratio for cruise, the disk loading, and this is for the hovercraft and or any kind of vertical craft, and then the thrust-to-weight ratio. We could debate all day about what the L over D should be. I won't spend time on that. I will talk about the thrust-to-weight ratio. McDonald and German used, this is how much you have to push down to go up. So if you got a vertical takeoff vehicle, you got to be pushing down harder than your weight. And McDonald and German used about a 10% extra, and all the literature says that's too skinny. 25% is probably more realistic. And most airplanes are down in the thrust-to-weight ratio of about a third, and ours clearly is, so that 0.34 at the bottom. So this is all the variables in the model, and basically what this slide's doing, it's saying the input variables, which are in the green, here I mentioned the energy densities, number of passengers. For the USTOL, how long do you want it to go? And then here's the outputs over here. It'll calculate all of these things. And this is not the world's most accurate model, but boy, it sure gives you a pretty good feel for what's happening. And all these other variables that you can see, like how much of the battery is used for hover or climb or whatever, all comes out in the wash in the model because they're needed. So does this model make any sense? Being an engineer, if I can't make my math match reality to some degree, I know I'm in real trouble. Problem is, there isn't a whole lot of data out there. There's fairly good data on the Robinson R44, and so if I tinker with the airframe weight fraction, in other words, I lower it, which is okay because this thing doesn't have wings, it doesn't have a lot of structure that a regular airplane does, and I used 55% originally. If you lower it to 0.3 to 36%, you can get the model to actually calculate a gross weight that comes out pretty well matching. And that gives, once you've nailed this down, it automatically gives a battery weight. And boy, that came out really close. That's scary for an engineer to come that close. And it gave a cruise time of 35 minutes, and they went 30 minutes. I felt pretty good about that. I mean, that's not bad correlation. I went out and tried to see what I could find on the EHang, and every time I looked at the EHang data, it was different. And that's not real surprising because it's still a work in progress. But if I lowered the airframe weight fraction down to 35%, it would give me a range of, whoops, okay, well, wrong button, 37 miles with no reserve. And if you have a reserve in there, it's down to 12 miles. So this is clearly possible for an urban environment. Now, this has one person, it's autonomous. You know, does any of that make any sense? Does the fact that all my friends call it a Cuisinart, does that make, I'm not addressing any of that. The eVTOL, which is a two-passenger vehicle, it comes down to a range of 17 miles with no reserve and minus 8 miles with a 10-minute reserve. So they aren't going real far with that vehicle, as best I can tell. The fun part of all this is these kinds of plots, which I'm going to show you a couple of. And what they are is, I put in the 3 different kinds of vehicles, and I said, well, if we're 2 passengers with near-future batteries, so this is 300 watt-hours per kilogram, what's the max range you can get? I have it miles over here, kilometers over here, and here's the energy, kilowatt hours. What you need to realize here, and not shown on here, is that if you're over here along this axis here, you're talking a 5,000-pound vehicle, okay? 2,270-gram vehicle, of which the batteries are a full third, so you're talking almost a ton of batteries, okay? That's a lot. This is a big vehicle to get these ranges. Over here on the other end, we're talking a 1,500-pound, so all of these points over here at the end are 1,500-pound vehicles. I almost wanted to go down to LSA size, but didn't quite. But you'll notice what this says is that a rotorcraft is going to be hard-pressed with 2 passengers, near-future batteries. You know, it's almost asymptotically at 50 miles, about 80 kilometers. eVTOL gets a little further. USTOL does even better. The other thing that's worth noting here is that a 200 kilowatt near future battery based on $100 per kilowatt hour is around $20,000 in batteries. So just some realities here, okay? So now let's play some games here. So this is the same plot I just showed you, but here's the same plot, but for current batteries, so 150 watt hours per kilogram. And I still have the 5,000-pound vehicle out here. I put a little scale up here for its weight. And you can see that the rotorcraft is hard-pressed to make 20 miles, okay? And that agrees with the other confirmation work that I showed earlier. So, you know, we aren't going real far if you want to do any of these. Now, for the urban environment that Uber's interested in, well, either one of these might do okay, but I still haven't bought off on this whole urban environment thing. I mean, if you want to go any distance, you got to do something much more interesting. So, I found this piece of data for Tesla Model S. It was really fun because not only is the Tesla Model S virtually a 5,000-pound machine, it has 100 kilowatt hours of energy in it, And on the ground, it'll do between 300 and 350 miles. I think that's pure coincidence, but it really looked good on that plot. So now, let's say we go to far future batteries, 450 kilowatt hours, watt hours per kilogram. Hey, things are getting more interesting. Now, you can go as far as my bladder can go, and that's really good. So, but the rotorcraft are still limited. They're never going to go real far, even on far future batteries. The eVTOL begins to be more realistic, but again, we're talking 5,000-pound machines, large machines out here. And in spite of the fact I've sat through 2 Uber conferences and they keep talking about these really large machines carrying lots of people, I'm having trouble visualizing those. So I went off and looked at what happens if you have 5 passengers with near future batteries. So here you can see all the distances are down. I mean, these are the best. Keep in mind, this is the best you can do. So you can do anything under these curves. You just can't get above them. And so a 200 kilowatt hour near future battery, again, we're up, well, we've still got those batteries, but now we've got a bigger machine yet because we're carrying 5 passengers. So altogether, the gross weight's 6,500 pounds. So that's pretty significant. Lastly, I did, somebody asked me, oh, one of your assumptions was you're only going to 1,000 feet. And if you're talking about these things going intercity, you got to get higher than 1,000 feet. So I said, okay, let's see what happens if we go 4 passengers and cruise at 5,000 feet. And you need big machines, but you can still get a pretty good range. Again, this is near future batteries. You can get a pretty good range of the USTOL. The eVTOL, very limited, 100 miles is all you're going to get. And these are clearly out of the running. This is, let's see, yeah, these are 3,000-pound machines out here now. So they're bigger, but not real big. Somebody else asked me, well, how sensitive is your model? So if we take a eVTOL, near future batteries, 3 people, and we change the reserve, remember I have a 10-minute reserve, up and down the reserve, 50%, it changes it a little bit. Hover time, that's really not to be worried about, even though I said something earlier about maybe it should be. The L over D is pretty critical here, and you can see that can make quite a distance. The L over D for climb, you aren't climbing that for that long a time, so it really doesn't make any difference. So this is whoops, too many buttons. This is a USTOL versus takeoff ground distance. So USTOL can get off the ground really nicely, and the more power you have, the shorter it'll get off the ground. What a surprise. Here's VTOL, it's 0 distance off the ground, and you can see if you get the USTOL up to the same power level, you can get off the ground in 50 feet, which ain't a whole lot of difference here. But the real thing is that if you compare these two, the USTOL has twice the range. So, if you want me to have a really tiny pocket airport, I can get there and still have twice the range if I go to one of this technology. And if you want to ease off a little bit, I can get the power required down to half and still have twice the range. I wonder if any of this is real. So, I'm going to come to that. So what are the takeaways from this? Okay, rotorcraft may evolve into usable short distance, but regardless of battery evolution, they're never going to go real far. They just aren't going to. Okay? Unless they go to hybrid, then they stand a chance. eVTOLs, they can be shorter mid-range, but they're going to be large, and they probably will require hybrid systems. I thought it was interesting at the Uber conference, Mark Moore is sitting on the stage with all these people that are building airplanes, and a couple of them are saying, we're going with hybrid because batteries won't do it. And Mark's saying, but our requirements require batteries. Okay. All All of them are going to be high-powered. Can you get rid of the noise? A couple people already talked about noise. I have no idea. I'm not a propulsion expert by any stretch. USTOLs really have an interesting potential. Nobody seems to be researching it too awful much, at least that I know of, that they've made public. So that'll be interesting to see where that comes down. And regardless of the mission, any of the missions I looked at, the USTOLs require about a third of the energy of the eVTOL. So there's a real potential here. Yeah, and depending on the takeoff distance, require much less power, and I showed that slide where the amount of power versus the distance. Takeaway 4, the whole idea of the airframe interaction I saw really lacking in the different visions that were shown at Uber. All these guys seem to be beating the air to death with a lot of propellers, and they aren't making good use of the flow. And I don't know what Pipistrel's doing because they won't tell us, but I hope they're doing something like this. I would like to think so. Yeah, so this just surprises me, and if you want to talk about propulsion airframe interaction, be happy to. This sentence took me quite a while. I wanted to see if I could get all the 3- and 4-letter acronyms in one sentence. So I managed to do that. So our project, which is the ideal, uses distributed electric propulsion with electric ducted fans, leveraging propulsion airframe interaction to achieve ultra short takeoff and landing. That's the translation. So thank you. So, does any of this make any sense? Well, like I mentioned, we built a wind tunnel. This is our wind tunnel. I can get between 40 and 90 miles an hour in it. I can get reasonable Reynolds numbers. It's all instrumented. I built wind tunnels. I built my first wind tunnel when I was 11 years old. I built wind tunnels professionally when I was a teenager. It's a good wind tunnel. It works really well. For a backyard operation, it works really, really well. So we started testing things. So I showed you in that earlier diagram something happening on the leading edge of the wing. And the question is, how do you put ducted fans on the front edge of the wing to blow the air over the wing in a way that really gives you what you want? We don't have the faintest idea. So luckily, I happen to know what fractional factorial experiments are. This is an L18 Taguchi fractional factorial experiment, which we ran in our wind tunnel. And we know what the best configurations are because we've got measurements that show it. So typically what we get out of the wind tunnel, this is just, we have thousands of curves. This is a typical, back up. You told me that would back up. There it goes. So this is an angle of attack versus lift coefficient, typical lift curve slope. This is with the electric ducted fans off. Plots up pretty well. If you lay a 2-pi line over that, it is actually reasonable and it's about right. If you turn on the electric ducted fans, you get this curve. Out here at the end, at 12.5 degrees angle of attack, there's a 63% increase in lift without loss of thrust. And down here, if you're at a really low angle of attack, there's actually an 88% increase in lift. So it does work, okay? So what are we doing next? Well, I bought this wrecked Jabiru. Somebody hit a pole with the thing, and the left wing was totally crumbled, and got it all rebuilt last year, and the FAA actually blessed the thing as a real experimental amateur-built airplane, so I had to give it a different name, so I called it the Jabberwatt. Right now, I keep hitting the wrong button. Well, anyway, right now, it has an internal combustion engine in it. We're going to continue the wind tunnel testing. Yeah, I keep hitting the wrong button. But anyway, we're slowly getting to the point where we're headed towards this, but the first thing we're going to do is string 6 of the engines, the ducted fans on it, and take measurements in flight once we get done with the wind tunnel testing. So that's pretty much where we're headed. Just an interesting thought. Somebody asked this question when I was doing this. This is the plot that I showed earlier with the current batteries, 2 passengers. This was the curves. The Jabberwock's really down here because it was an LSA airplane, so it's way down at the light end, near 1,500 pounds by the time we get done. And the weight fractions we're going to end up with are 46% for that and 33%, 35 kilowatt hours for the batteries. And that's just for doing, that'll be if we ever get that far. So again, from Willard Custard, speed of the air, not the airspeed. If you want more on any of this, if you go to my website, all the papers I mentioned are on the website. If you want the equations, you need to send me an email. And be happy to talk to you about any of this happiness. Got a few minutes for questions. Thank you.
Yeah, with the speed of the air versus airspeed, you now have, you're operating, at least the tests that you've shown are with regular airfoils, but obviously these are experiencing very different top and bottom. What are your thoughts about new airfoils for this?
Yeah, right. Thank you, Tyler. We started out with fancier airfoils with the flow going into the airfoil, and then we backed off and just went to these mods out in front because it was just too big to get our head around. The airfoil we're actually using in our tests is a good old NACA 4414 because that's what happens to be on the Jabiru, and we had to start someplace. So the configurations I've shown so far is just a small sample of what we've tried and thought of, and I have no idea. Is the bottom line. I think there's some real interesting things to happen there, but I don't know what they are yet. Yes, ma'am.
Great presentation.
Thank you.
Your comparison of the USTOL versus eVTOL is not quite complete, in the sense that the two can both get off the air, within 50 feet or something like that. But the climbing profile for the USTOL is really quite different. In other words, in the urban environment where we have all the high rises or various restrictions, you can't afford to climb like a fixed wing, like a USTOL type of climb. How do you?
One of the things I mentioned is I think this is probably a better configuration for intercity rather than intracity. I think I got those two right. In other words,
okay.
I don't know that this is the best solution for an urban environment, but it certainly is if you want to go any distance. Yes, sir.
For your Jabberwock, is it going to require full span flaps, do you think? Or are you intending to turn the flow
the reason,
everywhere you have the propulsors?
I'll give you a sort of circuitous answer. One of the reasons I end up with the Jabiru is it's an LSA, but it started out life as a four-place airplane. So the 1,320 pounds is sort of bogus because it really has a almost 1,700-pound capability. And plus, if you put Vince and I in that airplane with even a little bit of fuel, it's already over 1,320, so the LSA was bogus. But what's cool about it is when they took the back seats out, they left a big gaping hole where you can put stuff. The other thing is, this thing has flaps that go about 3/4 of the way out the wing. It's got really long flaps. Now, if we actually get to putting more than 2 or 3 propulsors on, I'm going to build new wings anyway because I don't trust the structure of that wing to take all the thrust forces. So in that case, we may end up with full flaps. Don't know. There's some really interesting features I didn't mention in this talk, but are in our patent application, is that you can throttle differently and actually execute a turn. You can throttle differently if you have an engine out. Doesn't care about an engine out, you just throttle back one of the others. You can throttle differently and change your lift profile out the wing to do all kinds of interesting things because these directly affect the lift on the wing.
Thank you very much. That was excellent.
Pleasure.